Hi there, my name's Andy Foster. I'm an ex-control propulsion astronaut instructor and ascent aboard specialist. I'm going to talk to you today about Space Shuttle ascent overviews. In other words, we're going to take a look at nominal Space Shuttle ascents. And I'll go through all what we're going to talk about in just a minute. Just to give you some of my background, I was a control prop instructor, which is an astronaut instructor, flight control instructor from 84 to 94. We did the main engines, the orbital maneuvering system, reaction control system, flight control system. I OJT'd on 41 Charlie. My first mission was 41 Golf, which covered in a book called Before Liftoff, if you want to go find it. I was assigned 62 Alpha, which we didn't fly, and then did Toys in Space 51D, and then went over to the FCA for a little while as an instructor over there, when we instructed flight controllers over there, ran the integrated sims. And then I was a short period in SNF's team lead before I came back and was probably my most favorite part of the job. From 90 to 94, I was an ascent aboard specialist. So my whole job was to be the subject matter expert on ascent aborts, contingency aborts, manual ascent, all that stuff. There was a lot of fun to teach. I also went to a lot of abort panels and flight techniques meetings as a training rep. And then I left NASA for 3 years, came back in 97, was in special flight operations safety, the lead engineer most of that time. I did a lot of the stuff in the mission operation or mission engineering room on the safety console, including being ascent entry qualified, and was a safety rep at a lot of panels, a lot of which had to do with ascent, as you might guess. So what are we here for today? We're going to talk about, first of all, just the basic parts of the Space Shuttle, make sure we're on the same page. We're talking about things and what they do. We're going to talk about how launch trajectories and orbits relate and how the shuttle achieved them. We're going to talk about the launch process, how it works, how MCC, the Mission Control Center, Launch Control Center, and the shuttle crew played together. And we're going to talk about what a nominal ascent is and why it was done the way it was done. And I'm going to show you the procedures for executing the ascent and the checklist. So here's a baby, the Space Transportation System, the NASA long word for Space Shuttle. And of course, we start off with the orbiter, talking about it, the airplane-like part, max crew of 8, 122 feet long, 78-foot wingspan, big payload bay, 60 feet long, 15 foot in diameter, that let it take payloads up to about 60,000 pounds into orbit. And those orbits were from about 100 to 312 nautical miles. And then on the entry, it could fly out a cross range of about 850 nautical miles maximum, so it had a lot of capability. And of course, it went to orbit because it had 3 main engines in the back that pulled fuel out of this big external tank. And as you can see, it's 154 feet long, roughly about 28 feet in diameter. That tank fed liquid oxygen, liquid hydrogen through umbilical doors that I'm going to show you, and big feed lines I'm going to show you in a minute. And then, of course, helping that, the engines alone couldn't have gotten it to orbit. We had 2 big solid rocket boosters, 150 feet long, 12 feet in diameter, each one putting out about 3.3 million pounds of thrust each. And each main engine put out roughly about 470,000 pounds of thrust each. On the solid rocket motors, there were 4 separation motors at the top, 4 separation motors at the bottom that helped pull them away from the tank once you decided you needed to jettison them. So just to go over the orbiter parts, the crew cabin's up here. That's where the crew was, flight deck, mid deck, and of course the mid deck had the airlock in it, and which let out the payload bay, where I'm showing you right here. And in this picture, I don't know what this payload is, but there's an orbiter docking system we'll look at next. Right there, you can use to dock with ISS, and this is probably an MPLM is what I think this is, a logistics carrier module going to station. And then the remote manipulator system, big robot arm that was controlled from back here in the rear part of the cockpit. Did let the shuttle do a lot of wonderful things nothing else could do. And then for atmospheric entry and control, just like any airplane, except airplanes have usually ailerons and elevators. In the shuttle, they were combined into something called elevons that control pitch and roll. And then yaw was controlled through a conventional rudder on the vertical tail, with one difference, and that is that the rudder could kind of split apart like that, and that would make it into a speed brake. While you're on orbit, of course, those aero surfaces don't do you any good. And so you need something to control attitude, and those are reaction control system jets or rocket motors. We had them located here in the forward pod, right up here on the nose. And there were two aft pods, one here and one here. There were 16 jets in the forward, 14 primary and 2 vernier. Each one of these pods had 14 jets in it, 12 primary and 2 vernier. The difference between the two is the primary jets put out about 870 pounds of thrust, which most of the muscle to roll and pitch the vehicle and yaw around. And then the verniers were for very fine attitude or translation if you needed it, and they were 24 pounds usually for attitude control. On the back end, if you needed to change orbits, you had the orbiter maneuvering system engines. Each one put out about 6,000 pounds of thrust. And we talked about the RCS and OMS. The nice thing about these two systems were they use the same propellants. Nitrogen tetroxide, which was the oxidizer, and monomethylhydrazine for the fuel. And back here in the aft, we could actually feed the OMS propellant to either just the OMS engines or the RCA, or hook them up and we could feed OMS and RCS in what we called an interconnect. And so here's a picture with the orbiter, and you can see the main engines on the back that we talked about. Right back here, they put out about 470,000 pounds of thrust each, and they get fed through big feed lines. I'll show you in a minute on the external tank through these two, what we call umbilical wells right here. These are E2 doors. They're open, of course, so you can get to the big feed lines when you put the orbiter on the tank, and then once you jettison the tank, they close up because you have thermal protection system tiles in the bottom. And I kind of mentioned the two aft RCS pods. They're also called the OMS pods, really. And this is where you have the RCS jets and one OMS engine. And there are two pods. That's why you say 2 and 28. So one OMS engine and 14 jets on each side. And there you see the orbital maneuvering system engines in the picture and drawing. And then finally, here's a drawing of the forward RCS pod with all the jets that it had. As you can see, the tanks and everything for oxidizer and fuel were up here, along with helium that was used to pressurize the system. Same kind of setup in the back. So here's the external tank, and it had the big LOX tank up front and the LH2 tank in the back. And in between the two was a section called the inner tank that hooked them up together and provided structure for the tank. The LOX fed back from the LOX tank through this 17-inch feed line all the way back to the back end here and up into the feed line that I was talked about for a few minutes ago, in through those umbilical doors into the orbiter. And then on the LH2 side, well, the LH2 tank is right here, right? So you just need a little short feed line that pops straight up and goes again into an orbiter 17-inch feed line. Back here along with the feed lines, there were two attach points, big explosive bolts held the orbiter on. And then we had another one up front to the forward attach point right here on this kind of triangular structure. And then the SRBs were attached with one forward attach point here in the inner tank, and then one back here on the dome. You can see right there where the tank kind of dome starts right here, and there's an attach on each side. So here's the solid rocket boosters. They were 4-segment boosters. Again, about 3.3 million pounds each. The interesting thing about a booster is notice that the grain here has a hole in the center that runs the entire length. So when you light one of these off, it burns the entire length and it burns outside in. And the shape of that cavity can be used to actually control the amount, the burn rate, which essentially controls the thrust that the solid puts out. And we actually did tailor the thrust down a little bit when we're going through maximum dynamic pressure, which I'll explain in a few minutes. So here are your segments, and then at the top we had a forward skirt that had some gyros and equipment in it, and then the frustrum where the 3 main parachutes were, a set of separation motors right there, the nose cap where you had the drogues and pilot chutes. On the aft skirt, another set of separation motors back here, and what you can't see is the thrust vector control for the nozzle system is in here, including an auxiliary power unit. It was like a shuttle hydraulic power unit, that was essentially turned on just before launch to control the gimbaling of the nozzle. Okay. So everything in the shuttle was controlled by computer. It was a fly-by-wire vehicle. That meant there was no direct, there was a stick and all that kind of stuff, but it was all just fed inputs to a computer, and the computer moved everything. Um, the GPCs, general purpose computers, we call them GPCs, were the brains of the whole thing. They were IBM AP101s. Each computer could run the same software set that every other computer could run. That said, the software was divided into two parts or two sets. The main software we used was called the primary avionics software set of the PASS. It was highly complex, lots of automation, coded, maintained by IBM, International Business Machines. The backup flight software didn't have everything in it. It had ascent and entry software, enough to control and take the orbiter up and deorbit it and bring it home. And it was a backup set coded initially by Rockwell. In other words, you had two different groups doing the coding for these two software sets, and the idea was that you wouldn't have the same kind of software coding errors because you had two sets of people doing it, make its way from one to the other. The BFS was a lot less complex in the past. It had the major functions, like I said, to handle ascent, deorbit, and entry, but some things had to be done and even flown manually because it was such a simple set. So it had OPS1 ascent software, OPS3 entry software, and RTLS software only. And if you want to know what RTLS is, go find the RTLS briefing. Now, this is over here on the right. You have the ops modes, or this is how the software was kind of broken down functionally. Pre-launch was ops 9, ops 1 was ascent, ops 2 was orbit, ops 8 was FCS checkout, ops 3 and ops 6, ops 3 deorbit and entry, and ops 6 is RTLS. So you'll hear me start talking in a minute about ops modes, and so that's essentially telling you we're using a piece, and primarily the PASS software that the BFS had. Again, well, actually, I think BFS had ops 1, 3, and 6, and PASS had all the others. And when we put the PASS in, what we did was we put the PASS into 4 of the GPCs, and then we loaded the BFS in the 5th. And all the computers in the PASS executed the software, the same tasks, talked and listened to each other, and actually voted on each other's health. In other words, they are all synchronized up together and doing the same thing. The BFS, while they're doing all this, is simply listening, taking information from the PASS when it needs it, and not doing anything unless the crew commanded it to take over. And the way they did that, there's a rotational hand controller at the pilot and commander station. Big red button on the top. If you pressed it and held it down, boom, BFS would take over. It would release the PASS set, and the BFS would take over, and off you went. So here is the, we're showing the Ascent software, since that's what we're going to be talking about is Ascent. And we talked about major mode or major function or ops 1, but within each ops mode there was a major mode, and this is showing you the major modes and relating them to different parts of the Ascent. So the very first one, when we got to ops 1, and I'll show you in the count where that was ops 101, which ran from launch T-minus 20 essentially to liftoff, and then at the instant of liftoff, the software automatically moded to major mode 102, and it stayed with you through first stage flight. Once you kicked off the solids, the software automatically moded to major mode 103, and that software had second stage guidance in it, and the software that got you essentially to main engine cutoff. Once you got to main engine cutoff, the software at after you separated from the external tank, it actually triggered based on a velocity away from the tank. It would flip over to major mode 104 if you needed an OMS 1 burn, and we'll talk about when you might need that in a minute, which is a burn using the OMS engines I talked about earlier. It would be in major mode 104 where you would do that. And then once you got through with that, or if you didn't do an OMS burn, you just coast in 104 until you got everything ready in the orbiter to go to 105. And then in 105, if you needed an OMS 2, and you just about always needed an OMS 2, in fact, you always needed an OMS 2, but you didn't always need an OMS 1. You do that in major mode 105, and then when you got done with that burn, there was a mode called 106, and really 106 was post-insertion burn mode. It was just to get the orbiter ready for orbit ops, and then go into ops 2, if you remember, which was the orbit software. These are the major modes. Now, we're going to talk about software functions, if you will, within, and these are important because essentially when I'm talking about ascent and flight control and how it got there, you have to understand these modules and what they did. And because, as I mentioned, the orbiter was fly-by-wire, so it was software and hardware flying the vehicle, no matter what, even if the crew was commanding. But generally, it was automated. And so the very first piece of software I'm going to talk about, I'm going to start in the bottom left-hand corner. We'll call it navigation. Essentially, navigation figures out where you are based on various sensors in the orbiter. It took its position from inertial measurement units. We'll talk about some of the other sensors that it could use. And it could figure out what your position was and what your velocity was. And it would feed that information to another module called guidance. And guidance would essentially, depending on whether it was open or closed loop, and we'll talk about that in a minute, would figure out what steering commands do I need to issue to flight control. And flight control controlled the main engine gimbaling and the SRB gimbaling and the aero surfaces if it was on entry, to make it go to where I want it to go to in the sky. Guidance figures out what steering commands do I need to get to where I want to go. Flight control essentially figures out what do I need to do, what do I need to move to make this happen. And then, of course, those commands are fed over to what we call the effectors, and that would be like the SRB or the main engine gimbals or the aero surfaces if it was aerodynamic flight, and it would move those. And then as it moved those, we had other sensors in the vehicle that would measure different, changes in translation or changes in rotation, and it would feed that information back in navigation, because that's essentially helping navigation software figure out where it is and what attitude the vehicle is in and all that kind of stuff. Now, I mentioned in the guidance software that we had two types, and one was called open loop and one is called closed loop. And open loop means there's no feedback. In other words, and the way that it worked in the orbiter was that at liftoff, first stage primarily, we simply had a table in there that said, if you're going this fast, because it measured velocity from navigation, pitch the vehicle to here, roll it to here, and yaw it to here. And this little table kind of shows you this velocity would be like in feet per second as an example. And you can see that 50 feet per second, straight up, 90 degrees, pitches straight up, roll 0, yaw 0, 100 feet per second, straight up, but it's rolling around. So that's telling you it's commanding the roll program. And then yaw is still 0, and yaw is usually 0 for most things, and at least in first stage. And so on and so on. So that's an open loop scheme. Just does what it's told. What's my velocity? Set an attitude. What's my velocity? Set an attitude. Closed loop, on the other hand, actually looks at where am I, where do I want to go, and what do I need to do to get there. And it does it cyclically. And so it continuously is correcting to get to a position and a velocity. And that is what gives you the fine control that you need to get into orbit. And part of the reason that you have these two schemes has to do with the fact that we had boosters, for one thing, that you can't really throttle, and then tons of thrust in first stage, and then less thrust in second stage, and more fine control because the engines could be throttled and they could be moved a little more finely and all that. And in fact, early on in boost stage, you're just trying to essentially loft quickly to get the aerodynamic forces down and then turn it down range to start, picking up velocity and minimize gravity losses. And that doesn't take a whole lot of smarts, really. But closed loop does, because then you got to get to this very precise orbital target. Okay, if you've never seen a space shuttle mission, most of you probably already know about this. There's launch, SRB, SEP, cutoff, and so forth, so on. Go up and do our mission, come home, deorbit, land, and then goes through a turnaround. And of course, the way it worked out for most of the program, initially, we always launched from the Cape, We landed initially at Edwards. We always had Edwards as backup. We landed once at Northrop. Didn't want to do that again because it got sand in the orbiter, couldn't get rid of hardly. And then essentially later on started landing at KSC, so we were launching and landing from KSC and keeping Edwards in our back pocket in case we needed it. So that's all I'm going to go through there, other than to make sure everybody knows vehicle processing, we probably do that. In transport and launch pad, pre-launch, launch operations, KSC, down to T0. At T0 or liftoff, then flight operations were controlled by Mission Control at Johnson Space Center. Program management also was located there, and so was training, which is where I was when I was teaching all this. So we're going to talk a little bit about ascent performance and orbital mechanics and how they kind of relate to each other so you understand some of the things about what we're doing. And this is a little picture of the Earth. You know it's not perfectly round, but we're going to say it is, and there's an equator. And we're showing you a picture of an orbit. And the high point of the orbit at the top is called the apogee, and the low point is the perigee. Now, then it's not top or bottom really, it's just high point, low point. Apogee at the high, perigee at the low. But there's the angle that orbit makes with the equator is called inclination. And so when we talk about these different inclinations, we're talking about the angle that the flight path makes as it crosses the equator. And that determines your position over the Earth when you're in orbit. Okay, it's measured in degrees. Okay, so we already talked about that. Talked about the high points, apogee, low points, perigee. So what's a circular orbit then? Well, orbits are by definition elliptical. A circular orbit is nothing more than an ellipse that has the two axes same size. And so a circular orbit is simply where your apogee and perigee are the same. That's it. Okay. So now you understand basic orbital mechanics. We're going to talk about some of the mechanics of launching into orbit. So when you have two bodies that orbit each other, really the only thing that matters when you're talking about the orbits and where they relate to each other is the center of mass for those two things. And the speed necessary to orbit, of course, depends on the masses and the gravitational attraction of the two bodies. That's really what drives it all. Okay, so we got the picture of the Earth down here on the left, and we're showing it, as you know, it rotates west to east. And since we're relating everything to the center of mass, that means that if I'm standing on the surface at any point, and the Earth is rotating west to east, and I'm, say, off at the moon, looking at the Earth, then I can see that I am moving with a velocity. That velocity, again, because we're relating an orbit to the center of mass, can actually help you get to orbit or make it harder for you to get to orbit, depending on which way do you launch. And so if you launch to the east, which is the direction of the rotation, you actually automatically, from the time you lift off, get some amount of velocity from the rotation of the planet. Okay, and it turns out that just because of the radius of the planet, that velocity is, of course, the fastest at the equator, and then it decreases as you go north or go south. At KSC, if you launch due east, you pick up 1,344 feet per second in what we call inertial velocity. Again, because we're relating to the center of mass of the planet. So it's what we call an inertial velocity. You'll also hear us use the term relative velocity. That's velocity relative to the surface of the Earth. But when you're talking orbital mechanics, the relative velocity doesn't mean anything to you, but the inertial velocity means everything to you. Now we had two types of orbits that we would fly into, and two ways of getting there, actually. When we first started off the program, we had a little more conservatism in the system, getting used to everything, and so we used a technique called standard insertion. In other words, we flew up to an orbital target and we kind of held, we didn't go as fast as we possibly could. And part of that has to do with being conservative about how much propellant you hold back for things to going wrong and that kind of thing. But what the standard insertion did was it put us up, not quite at apogee, but when we shut off, if we wanted to stay in orbit, we were going to have to, or at least a safe orbit, or we were going to have to do an ohms burn almost immediately. We needed more orbital velocity to get there. Now, and what this drawing is showing you is just a representative picture. M1 here is Meco for a standard insertion, and then we did later on a direct insertion. Remember we talked about height of apogee. Well, look how the height of apogee is. See, for standard insertion mission, your apogee occurred not too long after the main engines cut off. You got a lot more zoom out of the direct insertion Meco here, quite a couple thousand feet, probably 1,000 feet maybe. I don't know. I'd have to go look faster. And essentially the height of apogee is way around here. Okay. And the other thing that's funky about orbital mechanics is if I burn, wherever I burn, the result of that burn I'm going to see if I'm at an apogee or perigee is at 180 degrees out. If I start burning a little bit before, then I actually kind of move that apogee just a little bit as well, or move the point where it is in the sky. But and so we'll see how that comes into play later. But what we would typically do for a direct insertion, we'd burn here, we'd coast up to apogee and then burn here. Why? Because I wanted, if you follow this curve around, you could tell that the perigee is going to be really low. And so if I come up here at apogee and I burn, and I said the effect is 180 degrees out, I'm pushing perigee higher. And I'm going to kind of tend to circularize my orbit. For direct insertion, I come around here and coast all the way to apogee. I don't have to burn anything because main engines have done it. They've given me the extra velocity that I need. And then I get here to apogee, and I'm again going to burn. I'm probably going to circularize my orbit or raise it to whatever perigee I want to be able to work with. It could be that if you burn enough, you'll drive the other side to apogee. But anyway, that's how it works. Okay, when we're talking about inclinations again, what I want to show you is this one right here. This is 28.5 degree inclination. It turns out that if I launch and fly due east from someplace on the Earth, the inclination of the orbit will be equal to essentially the latitude. So what does that tell you? Well, KOC is 28.5 degrees north, and that works for whether you're north or going south. Now these other ones up here that the shuttle flew to, we did by putting in something we call IY steering, inertial yaw steering. We actually steered north to essentially force these trajectories to kind of bend upward like this to increase the inclination, as it were. And we'll talk about why you do that during ascent. It turns out once you get on orbit, your inclination is kind of set, and it takes tons and tons and tons and tons of propellant velocity to actually change the inclination once you get on orbit. If you want to change the inclination for an orbit around the Earth, you got to do it during ascent. It's really about the only way you can make it all work with the propellant that you have. And so this is showing, this green line here is showing a 51.6 degree trajectory. So this is an inclination that we would fly to ISS. And so ISS was way up here. This is about a probably a 39 degree inclination, I suspect. And then this is about a 28.5 degree inclination down here. So again, you got to change these during ascent. Once you get on orbit, you could expend every bit of ohms you had in the vehicle, and you'd only change your inclination by 2 degrees, which would be just enough to maybe see it on this map, but that'd be about all. 28.5. Okay, so this is a brain stumper, which really isn't much of a brain stumper, but if you look at this chart, tell me what inclination this flight was at. Now remember, well actually I guess I didn't tell you, so I will tell you. When I said the inclination, if you steer due east, would determine the orbit, it will. It determines the inclination. So if you look at a map like this one, if I'm flying a 28.5 degree orbit, what I will see is that the orbital tracks will go no further north than 28.5 degrees and no further south than 28.5 degrees. And so that tells you that we are looking at a picture of a 28.5 degree inclination flight, because here's 30 north right here, right there. If I had a 57 degree inclination flight or 51.6 like station, then you'd see those orbital lines go way up here and way down there. Okay. Okay, we already talked about this. You have to change it during ascent. It costs too much propellant to try to change the inclination when you get to orbit. The cost that you do that during ascent is by thrusting more north or south. That's propellant you could use to either go to a higher orbit or to take a bigger payload to the orbit that you want to get. So, like I said, nothing in life is free, right? And so if you want to change inclinations, you got to have propellant performance to get there. And we actually went to a lot of trouble to get the performance needed to boost the heavyweight ISS segments to orbit. And a lot of people always ask why Columbia didn't get there, and it's because it was the heaviest of the vehicles. And we could have modded it, but it was going to take a lot of work to get there, and so that's why the orbiters tended to go there instead. So the amount of inclination you can make is determined by how much performance you have. The other thing that kind of drives the inclination that you may launch to is something a little more practical than that. It is the physics, but it can also be range safety. And this is true for KFC because we had the capability from a physics standpoint to steer, actually we have one flight at 62 degrees typically, and so you could do that north or south, but because flights at those high inclinations, if we steered to the south right out of KFC trying to get to a high inclination, we would overfly parts of South America. And we typically did not want to do that because we didn't want to have something go wrong with our rocket and then dump it on populated areas. So that's why you would always see when we're going to these high inclination flights from KFC, we would steer to the north. Most of that's over the North Atlantic. And in fact, you don't even cross the coast of the U.S. until you get over 57 degrees. And even then, if you do, it's way up north in Canada, and you're really, really high. And we only did that one time. Range safety can play into the inclinations that you can steer out of a particular launch site, as well as just the actual physics of it. So, believe it or not, trajectories that we flew had a lot of work going into them to design them. So, for a nominal ascent, you're designing the trajectory to fly to an altitude and inclination to support whatever mission you had, depending on whether it's payload, Earth observation, research rendezvous, so forth, so on. But the other things we were always protecting for, as I kind of mentioned, was we didn't want to overfly populated areas, and we wanted to make sure that the external tank, once we shut off, and I'll show you where it would come down, did not come down into populated areas. The trajectories, Meco velocities, all that kind of things were designed to accomplish those things. Now, what about the intact reports? It turns out they were kind of the same way, but for RTLS and TAL, you didn't fly. You flew to something called a range velocity Meco target. That was a point in the sky that allowed safe recovery of the vehicle at a landing site. But we still did design those targets to protect land masses and populations from direct overflight and from ET impact. For abort to orbit, you flew to a trajectory that give you at least 105 nautical miles circular orbit because that was considered safe for 24 hours. But again, the targets that we flew to were designed to protect land masses and populations from direct overflight and from ET impact. Lots of things could influence that, Meco velocities, whether you did an ohm dump or not, that kind of thing. They're all cranked into it. And so this is showing you, I talked about direct and standard, and so this is showing you 28.5 degree, of course, this is due east trajectory out of the Cape. For a standard insertion, this was about the impact area the external tank would come down in. And then this is direct insertion. So again, you can see what the difference in having the main engines burn a little bit longer for direct does. Not only puts you in orbit, but it kind of hurls the tank a little further downrange. And then for 57 degree, which was typically the highest one we fly, standard insertion is here, and 57 degrees direct is over here, and actually in two areas, depending on the altitude. Okay. So for pre-launch course, you had the orbiter on the pad. There's our space shuttle on a mobile launch platform. The orbiter was stacked inside the over here in the vehicle assembly building. You can see a picture of one on the MLP, essentially coming out down the long road to 39A or B. And then over here at the pad, the rotating service structure, this is what was used to essentially place the payload in the vehicle more than anything else. And then there's the Launch Control Center, and this is where the firing room was. This is near the Vehicle Assembly Building, back at Cape. And then Mission Control Center, of course, this is over here at Johnson Space Center where I was. We have the MCC, actually several MCC rooms in here. And we also had, during the shuttle era, mission engineering rooms in here, and actually still do, but it's on the ISS side. So now what we're going to do is take a look at the pre-launch timeline, and you can see that it's broken down into two big pieces. And first is tanking to terminal count. In other words, from about 6.5 hours before down to T-minus 9 minutes. And then we have another piece of it from terminal count down to T0. And as you can kind of see, there's a lot more stuff happening as we get into the terminal count. So we would start off the tanking up here at T-minus 6 hours, about 6:30, with what we call the fast fill. We're putting high rate, putting the propellants in here at a high rate, so kind of filling those big tanks up. And as we get them toward the top, then we slow down, and we slow down the rate, and then we top them off. And you can see that right here. And then there's 1 hour hold in here. Not much going on in there, but essentially what you see here is replenish. In other words, these are cryogenic propellants, so they're kind of boiling off, and so we're just keeping a fluid flow in there to keep the top tanked while we count on down. The crew would be brought out at T-minus 2 hours and 25, put in the vehicle, do our comm checks here, and then leak checks for the cabin and cabin vent checks, get the ohms ready to go, do air to ground checks, and then we go into a 10-minute hold right here. And this was because, if you remember earlier, I said that one of the ops modes in software was called pre-launch ops 9. And well, ops 9 software is what's running all the way through this terminal count in the vehicle. When we get down here to T-minus 20, we are going to essentially load the ops 1 software that's going to complete the ascent into the vehicle. And so during this hold, we come out of this hold, we load up ops 1, and then we do it for the BFS, and then we configure the horizontal sit, which is essentially a display that has the landing site data for RTLS and TAL, get a weather update for the crew, configure the MPS system, and then it's not showing it, but there should be a hold right here at T-minus 9, and then essentially at T-minus 9 it goes to terminal count. And the reason we call it that is that on the ground everything has been controlled essentially by the guys in the Launch Control Center. Once we get down to T-minus 9 and from there on out, they start a piece of software called the GLS, or Ground Launch Sequencer. And the Ground Launch Sequencer essentially has all the automated actions that we need to do to get the vehicle ready. They're standing there monitoring. They could stop it if they see something. But essentially the GLS takes over the count. And then you can see here it says start drain back. What happens here is the replenish stops, and drain back is actually mainly in the LO2 tank. It starts kind of draining back propellant out of that tank, and it's all timed so that the amount it drains back, we know exactly how much that is and how much we have in the tank when we light the engines off. But it also affects the main engine to start because it changes the temperatures very, very slightly. But anyway, it starts to drain back. So this becomes a constraint, obviously, because if you drain too much LO2 out, then you can't go anywhere, or you shouldn't go anywhere, because you're not going to have the propellant you need to do it. T-minus 8 minutes, bring the access arm back from the crew. The GLS is checking essentially for orbital power. And then what we do is check in here the crew at about 6 minutes, I think, actually does APU pre-start in the checklist, And then at 5 minutes, they actually start the APUs. And this is showing you the GLS checking for those two events. And then as we get down to 3 minutes, yeah, you can see them right here. APU pre-start 6:15, APU start at 5, and then flash evap switches involves orbiter cooling, heater off. And then at T minus 3:55, if you watch the video, you'll see that we got the APU started, and so the system automatically cycles the elevons and rudder and speed brake, make sure they all go from stop to stop. And then once it checks the aero surfaces, it goes and it checks the main engine gimbals, runs them all from stop to stop. Okay. And then right around T minus 2:55, the LO2 tank should be at flight pressure. And that's when you see the beanie cap come off the top of the tank. This is essentially trapping O2 that's flowing out of the tank, boiling off. And then LH2 tank flight pressure at just under 2 minutes. And then we go down here, ground power goes away at T minus 50, and then at T minus 31 you see this RSLS redundant set launch sequencer. So at this point the orbiter software actually starts running the launch countdown, and what it's doing is it goes through and it runs that last 31 seconds including main engine start, and so the RSLS, the GLS is still out there, and GLS can issue a hold to RSLS, but RSLS kind of takes over the count, does everything it needs to do. If it finds a problem, it will stop the count and then go back to GLS and tell it to do what it needs to do, kind of in conjunction with RSLS. At 16 seconds before liftoff, you see the water deluge to protect the pad from acoustics, and then the sparklers come on because there's essentially the hydrogen's been recirculating through the main engines to kind of keep them thermally conditioned. Some of that is gathered right around, it can gather right around the main engines, goes out through a little vent, if you will, in the nozzle, and the sparklers come on to burn it off, so you don't have so much out there that when you light off the main engines it goes boom. And so, and then at T minus 6.6 the main engines would come on, the computers would watch them, make sure they go to 90% thrust at within 3 seconds, and if that occurred then it would continue with the count and light off the engines, or the solids, I'm sorry, at T0. And then of course everything happens really fast from there. Once the solids light off, you're going flying, the explosive bolts release, and off you go. So of course, the other thing I mentioned that earlier when I was talking about major modes, at T0, major mode 102. So the software goes into first stage ascent flight mode, vehicle goes straight up, clears the tower, and once it gets just slightly away, at least a little later in the program, in the beginning, we'd start off the engines about 100, and then once we got slightly away from the pad, they'd throttle up to 104, which is where we flew for most of the program. The next thing that's going to happen just shortly after liftoff is we do a roll program. Well, what's that about? We are rolling the vehicle around because we need to roll it to a launch azimuth. Again, if it would be due east for a 28.5 mission, further north if it was steering some other inclination. The other reason, though, that it was doing this roll program had to do with the aerodynamic loads in the wings, especially as you go through max Q. To be able to not pull the wings off the vehicle, the wings need to be at a slightly negative angle of attack. And the roll program was a good way of doing that and keeping the thrust vectors pointed up this way, which is where you want to go. The thrust vectors up this way where you want to go. And again, this part of the flight here in first stage is open loop. So essentially the vehicle is just going, okay, what's my velocity? And then it's setting a pitch, roll, and yaw angle. And so all this stuff is being handled by the open loop software scheme. Now, depending on the flight, where you were, somewhere between 30 and 50 seconds, you'd hit max Q, and it could be 30 to 0.83 Mach roughly. But what you're really doing is starting to become supersonic. That's putting a lot of aerodynamic loads in the vehicle. To reduce those, you throttle the main engines back down so you don't punch through with quite as much force. Additionally, what most people don't know is the SRB thrust was tailored or lowered in that region. It was designed to kind of not quite produce as much thrust and then come back once we got through max Q. The other thing that was happening was something called load relief. Because we're really loading up the aero surfaces, the elevons were moved in a way that they typically weren't, and would deflect essentially to reduce the loads on the wing. And load relief also was going on in the flight control software up until a total of about 90 seconds MET, or mission elapsed time. And what load relief is doing is it's trying to keep the orbiter in a band of G-loading, if you will, or acceleration in any direction, and it would move as necessary even off the guidance schedule to keep those loads in limits. That was for the first 90 seconds of flight. So once we got through maximum dynamic pressure, and actually the go at throttle up call would typically come just before you cleared it, but essentially it meant something early in the program, I think it was, but later on we just kind of considered it a comm check more than anything else. But the SSMEs would be back up at 104% full thrust, and the SRBs would be back at full thrust, and you're still flying your open loop scheme all the way up until about 2 minutes when the SRBs start to tail off. And the event that would tell us that was happening was something we call PC less than 50. We had sensors measuring the chamber pressure inside the solid rockets. Once that chamber pressure fell to less than 50 psi, 5 seconds later, the separation sequence for the solids would fire off, boom, blow explosive bloats, and those separation motors would fire. And usually that's about 2 minutes and 6 seconds at about 146,000 feet. And of course, what the solids are doing while the vehicle continues on into orbit on the main engines is they're free falling down until they get to about not quite 16,000, or actually we're a little below 16,000 feet. That's where parachute deployment sequence begin. Main chutes will be out at 5,500. They parachute in the water, get recovered by this tuck and then tug, and then go back to KSC. Right after SRB SEP, you're really close to about 6,000 feet per second inertial velocity. You typically pick up what we call 2-engine TOW capability right after that, which meant that if I had an engine out before this, I would have had no option but to do an RTLS, or return to launch site aboard. Again, that's covered in the RTLS briefing. Now I can go across the ocean. It's a lot safer, and that's called a TAL, or transoceanic abort landing. I picked up that capability right after SRB SEP. Now, the other thing that happened at SRB SEP was that the software transitioned from major mode 102, open loop guidance, to major mode 103, closed loop guidance. So now we're starting that fine control that we need. And then the other thing, that this was kind of late in the program, and it really had to do with going to ISS more than anything. We figured out that if we burn the OMS engines at about 10 seconds after the major mode 103 transition, we could actually pick up overall Ascent performance. Now, you're sacrificing ohms that you could carry to orbit and use there, but it was better to use it down here and make sure we got to the main engine cutoff that we wanted. And so that was called ohms assist. It was a 2 ohms engine burn, and the time on it varied. It wouldn't be any longer than about 2 minutes. The other call you would hear shortly after this was negative return, and that is telling you you can't go back to the Cape anymore if you would need to do an RTLS for some reason. And again, we'll talk about those in the RTLS briefing. The call would usually come around 8,000 feet per second, 8,200 feet per second, inertial velocity at about 4 minutes. That was always about where negative return was. And then as you continued on uphill, you'd get enough energy in the trajectory where if you lost a main engine, you could get to at least a safe orbit of 105 nautical miles. That point is called press to ATO. And then the other thing that would happen was we would do a heads-up roll. Now, people, if you'll notice early on in the program, we didn't do that. We flew all the way to Meco, and we flew heads down. And the reason we did this really had to do with saving some money. We were communicating during this part of the flight primarily through a Bermuda ground station. NASA wanted to shut that station down and save bucks. And when we had TDRS that we would communicate with on orbit available to us later in the program, and so we would roll heads up at about 13,000 feet per second, and just simply to pick up the TDRS. And so that's why we did it. Typically right around here somewhere, could be either side of it actually, you get a press to Meco call. What does that mean to you? If I lose a main engine, then I can just press on to orbit, and I should hit my Meco target, whatever that happens to be. Now, but you'll also get another point in the trajectory a little further down that's called single engine press to Meco, which means, hey, I've got so much velocity, I'm so high in everything that I can lose 2 engines now and I can still get to the main engine cutoff condition I want. Now, because the vehicle has been accelerating propellant the whole time, it's getting lighter and lighter and lighter, it's accelerating. It was actually designed not to go over 3 Gs. We didn't want that from structural reasons, but it was also a crew comfort reason. And so once it hit 3 Gs, we would throttle back the main engines to maintain 3 Gs. Now this would typically start about a minute before main engine cutoff. And if you're wondering what the trajectory looked like, this is showing you over here, and it shows you for 2 different inclinations. And this is altitude versus mission elapsed time with the Meco right out here. So you can see we kind of did this curve up and then hump over, and then actually a small dive. And this is to get us what we call the right flight path angle at Meco. Our main engine cutoff is Meco, and that flight path angle helped determine, along with the velocity, what the orbit was going to look like. And so Meco would typically occur about 25,800 feet per second. This is later in the program. Altitudes would range from 345,000 feet to 360,000 feet, depending on what kind of mission you were running, what altitude you wanted to, or orbit you wanted to get to, et cetera, and how much performance you had. All those things would determine that. Once we got to Meco, we would be on the tank for later in the program for 20 seconds. Kind of time varied a little earlier. I think it was 18. And then what's happening during that time is it's closing all the different valves in the main propulsion system that it needs to secure the engines and the propellant system. And then once it's got all that done, so it essentially you blow pyrotechnic bolts separate from the tank, and then the RCS jets fire down, pushing you up. That's called a -C direction or -C translation until you hit 4 feet per second. Once you got 4 feet per second away from the tank, the software would transition to major mode 104. Now, if you were doing a standard insertion, and well, I'll get back to, if you're doing a standard insertion, you're going to have an ohms burn in 2 minutes. So you had to kind of keep that in mind. If you weren't, then you didn't have anything going. The other thing that was happening late in the program at major mode 104 plus 2 was doing a plus X translation. You're firing the back plus X jets on the orbiter, and what you're doing is you're kind of sweeping the tank. In other words, you're pushing forward, so you're kind of scooting over the top of the tank, and that's because we had cameras in the ET umbilical well, and we were essentially getting photography of the external tank that we could recover and examine. So while we were wrestling with trying to keep foam from coming off, and that's what that was about. For a standard insertion flight, or if I had an underspeed, in other words, I had main engines go down early and didn't quite get the Meco velocity that I wanted, I might have to do an ohms 1 burn standard insertion. You would have to do an ohms 1 burn. That would be a Meco plus 2 minutes. If you didn't, if you had a direct insertion flight, if we were getting all the velocity we needed to get to at least a preliminary orbit from the main engines, then the next thing that was going to happen wasn't an ohms burn, because if you remember that diagram I showed you, apogee's way out. And so I'm just going to do what's called an MPS propellant dump, and that's because we still have liquid oxygen, liquid hydrogen in the vehicle, trapped in the lines. We're going to try to get it off, essentially to help us with maintenance later on and turn around, that kind of thing. And actually, though, you dump LO2 out the bells and LH2 out the side through a dump valve, and the LO2 actually would give you a little bit of thrust as it went out the back end. Now, later on in the program, what would happen after that, or while the MPS propellant dump's going on, actually, is we would pitch the orbiter up 90 degrees because you could see it out the top windows, and the crew would do photography of the tank. Again, this was to help us kind of gauge what happened with the tank while we're wrestling with the tank foam problems, but this became kind of a standard procedure. And once we got that done, well, we don't need the auxiliary power units anymore because main engines we don't need them anymore. We're not going to need the aero surfaces until entry. So we're going to shut down the APUs, and then orbiter cooling initially is called through something called the flash evaporator system, or FES. So we turn it on because most of the orbital cooling is handled in radiators that are on the payload bay doors, which we haven't opened yet and aren't going to open for a little bit. And so we got to have some stuff to keep the avionics cool and everything else. And so we use the FES for that. And then we take the software to Ops 105. Remember, if I told you earlier, 105 is a software mode that we need because it's got the stuff in it that's going to let us do an OMS 2 burn. And so we pro to 105. The MPS dump is complete, but we would still open up some valves at the back to kind of let it vent and inert, and because there will still be some propellant residuals in there, and then we power down any remaining electronics associated with that system. We close the umbilical doors underneath that had been open because we were plumbed to the tank, and then essentially we're going to prep for OMS 2, and we're going to burn OMS 2 in Ops 105, and then later on do Ops 106 just to get us ready for orbit. And again, I showed you these ET impact area charts. You can see where the tank would come down. And so here we are with our OMS 2 burn. We do the OMS 2 burn by using this display on the left. You can select how many OMS engines right here. You could put in the trim numbers, which essentially kind of tweak the angle of the engines, the weight of the vehicle, and the TIG. And then we have two sets of targets. We have PEG 4, and this lets you burn to specific orbital parameters. And then the other way you could do it is kind of a shorthand way, if you will, PEG 7, where you just put in, I want you to burn this much in each axis to get it not quite as precise as a result, but it was sometimes used because it was handier. Burn attitude and all that for the OMS burn here, 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 and then they track it over here. This shows them how much velocity they have to go in the burn, time to go, and all that kind of stuff. And HA-HP would show right here. This is your target HA and HP, and then current HA and HP. And so we'd use this OMS maneuver display, do the OMS 2 burn. Once we got done with that, we'd check out the OMS gimbals before we shut them all down, reconfigure the system, starting to get it ready for orbit, do an Ops 106 Pro, and then go in what we call post-insertion. And post-insertion essentially is just essentially getting the orbiter systems configured so that we're ready for orbit when the ground tells us that we have a go for orbit ops. Burning OMS 2, these are checklist targets here, and this shows you essentially this is a PEG 4 target set in this group right here, and a PEG 7 target set over here, and this is how the OMS gimbals worked. They're gimbaled just like the main engines were kind of gimbaled. So I talked about the procedures. Believe it or not, we're going uphill. This is your procedure set. This was a card in what we call the flip book, which was actually Velcroed up in the window. So if you want to step through real quick, here's the roll program, here's the throttle down, here's SRB SEP, here's the OMS assist, and this is telling you check your VAPTs. This is checking cooling. Not much to do if you don't have to abort. Roll to heads up is here. This is the manual throttle stuff we don't worry about in this lesson. And then Meco 25.819, Meco plus 20, ET SEP, what to do if you get a SEP inhibit, which we never saw. And then major mode 104 plus 2 seconds, plus X translation, and targets and ascent, so forth, so on. OMS engines off. Okay, because it's a direct insertion flight. Okay. The other thing that you did pay attention to in the flip book, these were the system flight rules. Now, we talk about these more in the abort lectures, but this is the type of abort you might do for these particular failures. Now, you can fly intact aborts because you lose main engines, but you can also do them for systems failures. And so here they are right here. Inside the checklist, the crew had this. These were the abort calls that we talked about. We didn't talk about all of them, but we do in the RTLS and TAL briefings. If you want to dial in on those, you can see what all these calls mean and how the crew managed them. But essentially, the column here on the left were the calls they get on going uphill. They wouldn't get these over here unless they were flying TALs. And we're not going to worry about those today. Okay, fans, that's all I've got for you. If you have any questions, contact me here at shuttlet0@gmail.com. Hope you enjoyed it and hope you learned something, and give me a shout out. Other than that, hope you'll go see some of the other briefings here on the site, RTLS TAL, ATO AOA, and even contingency aborts. See you later. Bye.